Good morning, good afternoon, good evening. I invite you on the discussion panel entitled The Power of Metal Powders. My name is Marcin Lisiewicz, and today I have a pleasure to be the host of the panel dedicated to metal powders. As we all know, metal powders play more and more important role in various production sectors. Therefore, we would like to discuss this topic today. We want to discuss about the equipment used for manufacturing of the metal powders, about the processes of manufacturing the metal powders, and also about the properties of the metal powders used for additive manufacturing. There are two experts with me today. They are both online. First of them is Professor Todd Palmer from Penn State University. Todd, would you like to introduce yourself in a few words?
Oh, yes. My name is Todd Palmer, and I am a professor of engineering science and mechanics and material science and engineering at Penn State University in University Park, Pennsylvania. I have a wide range of experiences. Primarily, I have experience in welding and joining and in metal powder characterization. And so that is sort of where I came into the additive manufacturing field, sort of as background there. And I've worked for about 25 years in the field. I started out at Lawrence Livermore National Laboratory, and I came to Penn State's Applied Research Laboratory, and I worked there for about 10 years before moving into my current academic position.
Thank you very much, Todd. Our second expert, Dr. Amir Abid from Retech Systems LLC. Amir, can you please say a few words about yourself?
Thank you, Marcin. Thank you for the invite, and I appreciate being part of this panel discussion. Looking forward to having this conversation. My name's Amir, as you mentioned, Amir Abid. I am the Director of Powder Products and New Product Development at Retech. And my background is in materials and material synthesis. And I have been in the additive manufacturing space for about 7 years now, and looking forward to having this discussion.
Thank you very much, both gentlemen, for your introductions. It's time for the first presentation to be presented by Todd Palmer. It promises to be very interesting speech, so it will be about the properties of the metal powders used for additive manufacturing. It promises to be very interesting speech, so I don't want to take any more time. I don't want to extend it. I pass the floor to Professor Todd Palmer. Todd, the floor is yours.
Yep. I'll try to keep it within time. I have a tendency to get a little chatty on the topic, but I do want to talk a little bit today about some of the work my group's been doing and some of the issues that I see in the characterization of metal powders, particularly for additive manufacturing. And sort of to say that they're just for additive manufacturing is rather broad, and probably a little too broad most of the time when we think about it, because additive manufacturing processes, especially for metallic materials, can be divided for the most part into 2 to 3 different major categories. First one being directed energy deposition, second one being powder bed fusion. Binder jet printing could be considered a third one, as more of a solid state process. But what you're doing with the powders is very similar to what you do in powder bed fusion. So you can tend to bring them together that way. So I listed a number of my contributors. Those are primarily students that I have that are working in a number of different areas. A couple of them are at the National Institute of Standards and Technology. And so one of the things, which is a good segue into another point that I am trying to make in talking about this topic, is really the need for how do we approach standards for metal powders and how that is going to really impact what the powders will look like over time. So sort of what I want to talk about is a couple different things. There's some real challenges and complexities in using powders. Many that we tend to take for granted because we're so used to looking at casting and wrought-based processes, which we've really had about 75 to 100 years to really implement really optimize them to really understand in a pretty good fashion what's going on with them. Now, when we start looking at powders, there's that complexity, but how do we characterize what the powders look like? And so I want to just do a quick review of some of the traditional powder characterization tools that are out there, and then move a little more into some of the more advanced tools that we're starting to see in use. And these are, for the most part, powder rheology based tools that really look at how powders behave on a little more of a bulk scale. And then one of my real favorite topics and sort of pet peeves, especially talking with some of my students, is how do compositional variations impact the powders? Because we always really tend to think about, we're characterizing the powder, we'll take flow rates, we'll do different things with how the powder behaves. But a lot of times we forget the complexity of the melting and the fusion-based processes in additive manufacturing and the role that things we didn't pay attention to before have. Nitrogen in martensitic grade stainless steels, the presence of high levels of oxygen, whether from melting practices during the atomization of the powders or from oxygen pickup, have an impact, and they start to produce oxide inclusions. And then some secondary phases. And then I want to follow up at the end with sort of future directions and road mapping events that have been done, and how we're really not following through on these events that we have. So one of the places that we really can start as far as the challenges is we want to take a maybe a little closer look at what do we typically use for AM processes. And if we go down the list, and so we have what could be considered a wide range of materials, we look a little more closely, we tend to see that the materials are all existing alloys. They were chosen primarily for their weldability and their availability. So there was really, when we started choosing materials for additive, we really took what was probably the easiest road. It was what was available out there and what we knew that would melt without cracking or having undue defects. In the case of aluminum, we actually chose casting alloys to use. So, but the issue becomes, as materials scientists, and Amir can definitely vouch for this in materials, is we are very concentrated on process structure, properties, and performance. And so when alloys are designed, processing has a means to do that. We've skipped that step in the additive process. So what we're using are alloys that haven't been optimized for additive. And if we take a little closer look at the complexity of the process, it really drives us to see why there's a high level of uncertainty, there's a high level of scatter in properties. The materials don't always behave the way we think they should. We see variability between heats. Because if you look at the complexity, you look at it as a circle, we're doing a lot of different things to the materials. Not only sort of the materials chemistry compatibility, but the fact that we're using feedstocks, that we're melting a feedstock with a laser, that we have high levels of melt pool dynamics going on. There's a lot of convection, there's a lot of mixing, there's a lot of segregation that goes on as we solidify the materials. We're susceptible to cracking, we're susceptible to a range of defects. Now, post-processing and where SECO and some other players come in is how do we post-process away these defects and these inconsistencies in the microstructures to obtain the properties. And for me, that's one of the big areas to really start thinking about as we look at additive, is the idea of developing new alloys is a long drawn out process. Even if we try to use machine learning and we sort of try to convince ourselves that we can do it more quickly than past generations have, the requirements for developing design allowables are far too stringent, especially for critical application, for that to happen in any reasonable time frame. Our really best hope is to start thinking in terms of how do we post-process. Now, where I'm going to want to concentrate a little more today is on sort of this idea of powder feedstocks and powder characterization tools that are out there. So if you're interested, I've added a couple papers that came out of my group specifically, a little self-advertisement there, but we've been thinking about some of these areas and how to characterize them. And so those are available if you're interested. But when we start thinking of powder characteristics and how they impact bulk flow properties, so when we we characterize powders, we really characterize them in two ways. We characterize them first as particles, and second as these bulk powders. Now, bulk powders are the ones we're more familiar with when it comes to the powder metallurgy side, where we're interested in flow rates, angle of repose, apparent density, tap density. When we think of particle characteristics, we tend to really only think of particle size distribution in a lot of cases, because it starts to get really hard to start thinking in terms of morphology, surface energy. The composition is something that we tend to push off into more the material side. Internal porosities are another one. And so they are sort of all there. Now, as we do this, I want to discuss some of these characterization tools a little more in terms of a case study that we've done, where we're looking at the same material. So this is a 316L stainless steel that two heats were atomized with nitrogen, another with argon. A couple different things we saw was this role of nitrogen, which I'm going to come to a little later, is we see that it's almost an order of magnitude different when we go from the argon atomized to the nitrogen atomized. It's a 9 times difference. It may be a small number, but it's a huge number in terms of nitrogen potential. And if we look even at the oxygen levels, they are extremely high as far as oxygen goes compared to rot. This results, when we start looking at it a little more, is a significant difference in yield strength, which is something we caught on. So we were interested in why that would be after the yield strengths were obtained after a powder bed fusion process. So we wanted to look at particle size distributions. Now, when you look at particle size distributions, you can look at laser diffraction or image analysis. Image analysis is a tool that we sort of brought on, first and foremost, not to really look at particle size distributions, but to actually start looking at the morphologies, because we see these are actual images of gas atomized powder particles. So the idea that they're all completely spherical is not quite true. And so we started wanting to capture that, and we captured it in a number of different ways. We use terms like convexity, basically aspect ratio, and circularity. So what these are ways of thinking about the roughness of the surface, or how these particles vary from what we consider to be a perfect sphere or a circle. In this case, we're looking at them in a two-dimensional, basically they pass light through them, and so it's a two-dimensional representation of the particle. So it's not completely there, but what we tended to start seeing was the way we atomized them gave us differences in the amount of spherical particles. And we tend to look at them in terms of this cumulative distribution. It allows us to see differences between the behaviors a little more easily. Now, if we use our traditional powder feedstock characterizations, and these are, for the most part, what are considered in more traditional press and sinter powder metallurgy, whether it's Hall flow tests, apparent density, you can extract a Hausner ratio out of the apparent density to tap density ratio, angle of repose. What we tend to see is that there are some differences. They're fairly minor, really. They don't really change very much between them. But what we did see was we saw that yield strength difference. We see the difference in morphology. And as we start looking a little deeper, we're going to see some other differences. Now, the one that we find is in some fields, they'll tell you that the angular repose really tells you nothing. We're actually seeing it as being a little bit of an indicator. It doesn't really tell us a whole lot, but if there's a difference in the powders, we tend to sort of find that a little more easily in the angular repose, and we start to see that there is a slight difference here. It's not very much in this case. We've seen much more of a difference in some other powder systems, especially when we're looking at it. But in terms of additive manufacturing, those tools aren't really all that useful. They don't really replicate what the powders are experiencing, whether we're dragging a blade across a bed of powder in order to spread it out to make sure it's uniformly spread. It has the same packing density so that when we melt it with the laser that we see the same absorptivity and different things. Or in a directed energy process where we're worried about powder flow through nozzles and then how the powder interacts with the rather intricate components within the powder feeder. So this was, basically how is flowability defined? So if I would ask my students, the typical answer that I would get is the same one I would probably get from my 18-year-old or 14-year-old son. Basically, is that flowability is the ability of the powder to flow. And you have to ask yourself, what does that actually mean? And it's one of those ill-defined things. It's very similar. As I said, I have a welding and joining background. It's like asking a welder what weldability means. And you will get probably, you ask 10 different welding researchers, you will get probably 10 different definitions of weldability. You're going to get the same thing in powders as far as what flowability means. And it really depends on the process. So what we wanted to start doing was looking at different means to do that. And we found that some of the rheology tools that are out there probably represent a little better of what the powders are undergoing in additive processes than what we're typically seeing in more traditional press and center characterization tools, which, by the way, really only look at particle characteristics and not really these types of flowability. Spreadability is another term that sort of falls in there as being that type of very ambiguous term that people can get away with when they start talking about powders. But rheology tools are out there, and there's a couple different ways that they look at it. And it's something that you sit and think about, how do we pack powders? How are we spreading the powders? Where we start thinking in terms of how do we characterize a powder in a consolidated, unconsolidated, and a fluidized state. And in a traditional powder feeder used in directed energy processes, which you'll see is the powders experience all three of these as they're fed into fluidization chambers and through nozzles, and as they flow, you'll have that. Now, there are three primary tools that I see out there. There are other tools that are being developed, but these are more the traditional ones for powder rheology. Is a rotating drum technique. Basically, what is considered a powder rheometer, I consider it more an annular shear cell, and then a more traditional shear cell that allows you to measure characteristics like permeability. So these three processes are out there, but they tell us different things, and they give us different measurements. And when you really use these systems and you use the commercial systems, what you'll tend to find is you end up probably receiving about 30 to 40 different numbers that come out. And it's really unclear what those numbers actually mean. And this is where the issue of standardization and having the underlying science and the technical baseline for developing standards is, what is a rotating drum actually measuring? Rotating drum measures the angle as the drum is rotating. It measures the angle which the powder goes up the side, very much like a liquid. So if you're thinking of a sloshing fluid in there, it's the same type of idea. Now, the higher avalanche energy is typically correlated to the higher potential energy to initiate flow. So higher flow resistance, lower flowability. And as you start comparing these, what we tended to see in the cumulative distribution. So when you take these avalanche angle measurements, you need to take a rather large number, and it can vary. So different rotating drums will rotate them at different speeds to produce different conditions. And if you rotate it fast enough, you'll actually start to fluidize the powder, or basically elevate it, much like a fluidized bed, back into our days of working in those, or for people who work in that process. What we tended to see in this case, and what the rotating drum really showed us, was that there is a difference between the powders, and it really captured it as far as the avalanche angle that was found, with the argon atomized powder having really the best flow properties. Now, a powder rheometer measures it differently. It basically will take a blade and measure the torque of moving the blade downwards, whether it's counterclockwise or clockwise. You can determine these. Now, basic flow energy is the typical measure of flowability in these types of tools. What we tended to find is we didn't find a similar trend, which led us to really start thinking of what's going on, and led us into thinking more in terms of what about the individual powder particles. So we returned to that. We knew there was a difference in the morphology of the powders. We started to get interested in what's going on with the internal porosity, because a lot of the powder rheometers, a lot of the annular shear cells rely on force measurements. And they make some pretty gross assumptions at times on the mass of the powder. And so if you have porosity in the powder, the actual mass of the powder particles differs. And so we used the tools we had at hand here. And so working at a university, a major research university, we had some different tools. So we went to some other different departments and talked to them about how to do this. And so we started using micro X-ray computed tomography techniques. Basically, we were CAT scanning the metal powders. And we were able, when the CAT scans, to identify not only how they sat in a loosely packed state. Basically, we took a 3 mm straw with a 3 mm diameter and filled it with the powder. And we were able to identify internal porosity in the powder. What we found was the internal porosity of the powders varied, which if you go back to the annular shear cell or the powder rheometer, the actual mass measurements used to determine the basic flow energies was changing. And so we found that, and we also went a little further and started quantifying local packing structure. Now, in binder jet printing, this is an important consideration, probably a little more than what we see in more fusion-based powder bed processes, because the infiltration of the binder is really depending on the void spacing and not as concerned with porosity in the powders. What we did find was that the permeability, which is for the most part the ability of gas to flow up through and against a normal stress, we found differences between the powders as well, which is in part based on some size distributions that we see, and we see the equivalent, how the void spacings and how the powder's packed. So in our terms, it comes down to characterizing powders is probably a little more complex than just running a couple simple flow tests or apparent density or tap density, where we look at a range of different characteristics. And so what I want to move on to, and I'll move through this, I'm sure I'm taking more time than I should be, is compositional variation. So once you get past how the powders are reacting as particles or as bulk powders, you start running into the idea of how does composition change? Now, composition can change in a number of ways. I tend to find that the biggest issue of composition goes back to traditional melting practices and traditional metallurgical processes, and basically when we melt the feedstock. The atomization gas might have it. I tend to think the atomization gas probably has a little more of an impact, and I'll let Amir talk more about this, has more of an impact on the properties of the powder particles than the composition of them. Processing, depending on the process as well, you can pick up some gas, not as likely in my experience. And post-processing. So when you look at pH grade stainless steels, all of these things can contribute to some real differences. Now, we've been looking at it, and once again, I'll use a little bit of a case study. We've been looking at a number of different heats. And so we've started to take this approach. A lot of academic papers may look at one material and make some broad assumptions about the entire alloy grade. If you look at the allowable ranges that are the allowable ranges for compositions, which you tend to find are some pretty large gaps between them. You can have a 2.5% difference in chromium and still maintain and have that be considered, in this case, a 17.4 pH grade stainless steel. And we see a little bit of this difference as we go across these different heats. So these are actual heats of material that we've tested and looked at. Now, the other one that we found, manganese is one, but nitrogen can vary significantly. And nitrogen is a very potent austenite stabilizer. So if we look at the way that welders look at nickel equivalents and chrome equivalents, we see that our nitrogen composition is multiplied by a factor of 30. That gives you an idea of how potent, empirically at least, nitrogen is in stabilizing austenite. And we definitely see that here with the high nitrogen ones. When we looked in the as deposited condition, we had about 81% retained austenite. It's a martensitic grade stainless steel, and it was primarily austenite. That tells us that there's a big difference, and we can go from almost none to 81%, and there's the same grade of alloy. And if we look at the computational thermodynamics for it, what we tend to find is there is a potential to solidify some high some high temperature delta ferrite at the low nitrogen, but that disappears as we add nitrogen. So same alloy can be sold the same way, used the same way, can behave in completely different fashions. And what we tended to find was that the aging responses were changing, is what was really, for pH grade stainlesses, the aging is really where we have it. And what we saw when we had these high nitrogen levels were over 200-degree differences in our peak aging temperatures as we started looking at it. This is a huge difference and something that, for an industrial practice is just not acceptable. It will never fly. And especially when we started looking at tensile strengths, because with that much retained austenite, the material actually took on transformation-induced plasticity effects. So it was totally different than what you would see in a traditional alloy. Now, oxide inclusions are there as well, and where we concentrate on the oxygen, there are these higher levels of oxygen. Now, we looked at duplex stainless steels in this case, so I'm going to switch between some different alloy classes here, but we started seeing some differences. So when we started looking at the powder, so this is an individual powder particle that has been cross-sectioned, and that is actually a pore within a powder particle that we're able to resolve. Now, we saw high levels of oxygen and small inclusions, both internal and external, and even within the pore, to tell us that it's not really just an oxygen surface pickup of the powder. The unique thing about the oxide inclusions that we found in the powders is that they were primarily amorphous, and that has to do with the rapid cooling rates in atomization processes. Now, when we processed them with directed energy, what we found was the oxide inclusions stuck around and they started to really evolve. So they took on different crystal structures, a spinel, which is a chrome manganese oxide, rhodonite, which is a little more manganese oxide rich, but it still maintains some of the amorphous properties. And we tended to see that they acted as inclusion sites for austenite forming in the duplex stainless steels. So differences that really are there, and then they evolved, and after hot isostatic pressing, they took on much more equilibrium type processes, but they're still present throughout the materials. Now, as we change materials, this is going back to those austenitic stainless steels that we started looking at. You also see them, and you see these oxide inclusions form. And once again, these are from powder bed fusion-based processes. The oxide inclusions themselves are amorphous once in the as deposited state, which leads us around to starting to try to think about how do amorphous oxide inclusions act as strengthening agents, or are they strengthening? Are they good or bad? And they can change. We've been seeing that they're not really acting in a favorable sense. I don't have time to go into a lot of the details. We're starting to publish a little more on that, and I'd be happy to talk to anybody about where we're going. But nickel-based alloys are also, and this is one where that difference in composition is having an impact. And we were primarily interested, first off, in Inconel 625, very common alloy. Different iron contents were our initial one. We didn't look at the nitrogen levels at first, but what we found was that they had an impact. Now, this was our first thing that we found was, even though they're the same alloy, they have significantly different grain structures. These are electron backscatter diffraction patterns that allow us to see grain structures and crystallographic texturing within the material. And what it showed us was huge differences in the grain size, which tells us that we should see differences in strength. And we saw about a 25% difference in yield strength between them. But we were more interested in the secondary phases that were there. And so we went to additional higher energy tools. So we went to actually a synchrotron, which are particle accelerators that produce very high energy X-rays. And a synchrotron cost a couple $2 billion to build. So the US government builds them and makes them available to users at Argonne National Lab, at Berkeley, at Brookhaven. There are several within the US and at Stanford. And we use the X-rays that come off the particle accelerators to help us identify different phases that were present. And what we found was that the phases, that there were any number of different phases present, and they varied with these different compositions. Once again, even though they're the same alloy. And allowed us to see these different phases that formed and how they're really being impacted by that. And so these are transmission electron microscopy images, and these are selected area diffraction patterns that allow us to identify the actual crystal structure within them. And from that crystal structure, we can identify what the phases are. And what we found was that this Z phase, these are nitride-based precipitates that are a couple hundred nanometers. And we found that they are having different impacts on the material and really impacting some of the high temperature properties, which is an area that we're looking into now. Now, as far as future directions, this is a little bit of self-advertisement. Really about in 2015, we put together roadmaps for looking at the next generation of additive manufacturing materials. And really what we're sort of seeing is, a lot of the same thing, but what makes additive different is this idea of integrating design directly into materials processing. So in an additive process, you're actually running through all the materials fabrication at the same time you're making the part, which makes it that much more complex of an endeavor to undertake. And so we've been thinking about this now. A lot of the recommendations, a lot of the thrusts identified in sort of the road mapping efforts really haven't been undertaken in really the same ways. And one of the ones here, especially for today, is, how do we test feedstock? And that is really sort of one of the hurdles that I see moving forward, is being able to standardize and, for the most part, put certification and standards together that have a strong technical underpinning. So that is the end of my talk, and thank you for your time.
Thank you very much, Todd. It was a really very interesting presentation, very informative and educational, not only for me, I hope also for our audience. We will get back to it right after our second presentation during our questions session. In the meantime, I encourage our audience to write the questions on our chat. Our experts will try to answer all of them later on, so don't hesitate, just write them down on the chat. Ladies and gentlemen, now it's time for our second presentation, to be presented by Dr. Amir Abid. And this presentation will focus on the equipment used for powder manufacturing, and also metal powders manufacturing, and also about the various processes of manufacturing of the metal powders. Amir, the floor is yours.
Thank you, Marcin. Appreciate it. Good morning, good afternoon, good evening, the audience listening in. It's my pleasure to talk about powder production for additive manufacturing. And so this talk will be broken up into roughly 3 sections. I will introduce the topic of powder usage in industry in general and what's driving the growth of new technologies for use of various different powders. Talk a little bit about some of the characteristics of powders and how they're influenced by the process method that we use, different atomization techniques, etc. And then I'll wrap it up with a case study describing some of the work that's been done at RETEC on developing the next generation of atomizers to support the industry's needs. So I think it's fair to say that there's a lot of growth and interest in powders, of course, driven by additive manufacturing and various different other methods that allow us to come up with innovative products that we might be limited with if we were using standard press and sinter methods, or even cast and forged technologies. And so this image on the screen describes a evolution of powder. Powder has been used by humanity since 1,000 years plus, where we used iron powders to produce structures that were large. More recently, in the last century, we've used tungsten powders to make tungsten wire for light bulbs, and the list goes on and on. But more recently, over the last 20 to 30 years, we've developed new technologies where we can use powders to build layer by layer and build complex structures using additive manufacturing or metal injection molding. And so there's a lot of excitement in the various different methods by which we can make unique powders. More recently, there are market drivers that encourage the industry to produce unique alloys in various different forms. Todd did indicate that alloy development is not for the faint of heart, and so it's an important point to make that the life cycle of an alloy development can be long, but still there's quite a bit of interest in using maybe existing alloys, but then applying the various different processes unique for additive manufacturing to get the unique properties that we're looking for alternative energy solutions, possibly in healthcare. Of course, with the pandemic over the last few years, there's a lot more interest in distributed supply chain, and powder technologies allow us to achieve that goal, as well as some high temperature, high performance applications like hypersonics all drive the need for producing better solutions for powders. So how are powders made? Of course, if you think about flour, which is maybe one of the most basic food groups for humanity, that's been done through a milling process. But sticking with metal systems, metal powders, gas atomization and water atomization are some of the main ways in which metal powders are produced. There are also other technologies such as centrifugal atomization and spheroidization. And so there's a variety of different ways in which we can produce powder, but each of these ways have some unique performance characteristics, and not all methods are suitable for a certain end product. I'll touch on that in a few minutes here.
Okay.
To give you an idea on the various different broad technologies, I show three main methods by which we make metal powders. By far, water atomization is the largest by mass of powders produced worldwide. A lot of the steel and copper and various different non-reactive powders are produced via this method. And the process is using a melt where we introduce a liquid stream into a high-pressure jet of water, and then you get morphologies that are irregular, suitable for press and sinter applications. But when the application requires better flowability or higher packing, then gas atomization is utilized. And we tend to get more spherical powder, which allows for better flowability and packing. And for some processes where the reactive nature of the material requires a different technology, plasma atomization is also used. And plasma atomization also produces spherical powders of relatively narrow particle size distribution. So, coming back to these various different methods by which we produce powder, there are different characteristics that are significant based on the process that's used. For example, the morphologies are different between these technologies. Geometric size, standard distribution, which is the width of how broad or narrow the particle sizes are of the powders produced, are important as well as how fast we can produce these. Some technologies inherently, based on the way they're configured, are slower in terms of melt rates and atomization rates, and that will impact the cost of the powders produced. And then Todd, in his previous talk, described in an excellent way, the chemistry matters. Chemistry significantly matters, and the different processes that we use will impact the chemistry, whether it's the amount of oxygen or nitrogen pickup in the process, the ability to have various feedstock, and how we can manipulate the final powder chemistry based on the feed material that's going into the atomizers will also influence processes. And then finally, efficiency. Generally, atomization processes have a broad range of efficiencies, and that'll again drive cost. For example, For milling processes, comminution processes, the efficiency is relatively large. The input of energy to the breakup of particles is relatively large, compared to, for example, spheroidization, where a lot of energy is required to achieve the final morphology. So those factors need to be considered as we look at the overall performance and cost of powders produced. And so some of the key characteristics for additive manufacturing and other powder processes are described in this, where it's relatively lower cost to produce irregular powders than powders that have a very high sphericity and a narrow distribution. And depending on the technology that's used, there will be different requirements for the powders. For example, in a PM process shown on the left, we can work with relatively large particle sizes with broad distributions, and that allows us to use manufacturing methods like water atomization, relatively lower cost process. But as we go into additive manufacturing for powder bed processes like E-beam or laser, the requirements become more stringent, and there's additional processing, additional technologies that need to be applied to achieve the powder characteristics desired for these processes and modalities. And then as we go to even finer powder, so that's been a general trend in the industry, where there's a larger need for producing finer metal powders for metal injection molding, for laser powder bed fusion and binder jet applications, where we're trying to improve the surface properties of the final part that's been printed, or we need the flow characteristics in terms of binder jet to be able to get the final part performance. So the industry is constantly moving towards different powder characteristics, and it's important that we come up with atomization methods or technologies that meet the industry need. To just describe what I mean by powder distribution, on the figure on the top left shows what typical atomized powder distributions look like. So it's important to understand that when we melt and atomize powder, you don't get a single particle size. Typically, we characterize powder by the mean particle size, which is the D50, and then the spreadability of that distribution by D10 and D90 values. For example, on this image, you can see that the mean particle size produced is about 1,000 microns, but you have a spreadability that comes with the powder. And so normally when we are selecting powders, we need a relatively narrow distribution to be able to meet the performance required for flow or packing or other characteristics based on our modality for printing. And so you can imagine that only a fraction of the actual as-produced powder gets utilized. Here we describe the main technologies used for producing reactive and refractory metal powders, and to show that there are different distributions for different methods to produce powder. On the x-axis, we show the particle size, and the cumulative percentage of that particle size is shown on the y-axis. And you can see that for plasma rotating electrode atomization process, you have relatively coarse powder that's produced compared to plasma atomization using a wire, for example. We can achieve finer powders. The challenge that we have generally is that the distribution that various different printing techniques need are narrow. And so depending on the process and the distribution that's required, the atomization methods can be selected. Here I show for binder jet and laser powder bed fusion on the left, a small fraction of the overall distribution gets utilized. Whereas if you were trying to produce direct energy deposition powder, utilizing a plasma rotating electrode, you could use a large fraction of the as-produced distribution. Coming back to switching gears from distribution to chemistry, this is also extremely critical. Todd explained in his talk really well that standards are critical in being able to achieve the performance that we need to specify for our powders, and all of these will of course be be impacted by the overall cost. So we have to consider the cost as well. Interstitial impurities, elemental purity of the feedstock is going to be important, as well as any inclusions, as Todd mentioned in his talk. For reactive powders, we have another layer of complexity compared to non-reactive powders like iron and nickel, is that we have to then achieve extremely high pure environments, whether it's an inert gas or a very clean feedstock that we start with. Also, the wetting components have to be considered. For reactive metals, ceramics are a challenge to work with because the reactive metals react with the oxygen in the ceramics, oxygen and other interstitial gases. And so the availability and purity of the feed also becomes an important input. As I mentioned, that what you start with will influence what the final powder chemistry ends up being. So being able to source high purity feedstock is important, but with the high purity comes additional costs. So there's a balancing act that the industry performs to be able to maximize the value that we can produce for our customers. So now switching gears slightly from what are the methods by which we produce powder to what RETEC is doing to address some of the new powder demands in the industry, there has been an uptick in interest in producing refractory and reactive metal powders at scale. And so at RETEC, we have developed a plasma atomization method where we can use bulk feed of a variety of different forms, scrap as well as ingots, to melt, hearth melt, and then atomize in a non-contact way. And so this allows us to produce high purity refractory and reactive powders such as titanium and other systems that are similar. For example, this gives you an idea of some of the inputs that are required for a plasma atomizer. Typically, we work with a high-powered torch, a plasma torch, and we use high-purity helium to be able to minimize the reactivity of the gases with the powders produced, as well as various different mass flow rates for the atomization gas to achieve the final powder distribution. Just to remind everyone, this is a titanium 6-4 alloy that we were atomizing on this system. And then this data provides some insight into the various different particle size distributions. Just to remind the audience, as you can see, if you're looking to produce fine powders, there's a certain percentage of material that you will be able to utilize of the distribution. But this distribution is very typical for other atomizers that produce titanium. So the results are encouraging for what we see here. And then just to overlay the performance of the plasma gas atomizer to some of the other standard methods by which we can produce reactive metals, you can see that the plasma gas atomizer spans the general range of state-of-the-art technologies such as PrEP or plasma atomization. In terms of chemistry, we were able to also achieve the chemistry targets for the Ti-64 alloy, but I will caution that based on some of the points that Todd had mentioned earlier, that it's not sufficient just to look at the chemistry within spec, but we'll have to look at some of the nuances of oxygen and nitrogen, as well as some of the shifts in the chemistry based on the alloy system. Hall flow, apparent density, and tap density as standard methods by which we characterize the physical properties of the powder, and they're within the state-of-the-art for Ti-6-4 commercially available powder. In terms of morphology, we do see mostly spherical powders that are produced with a little bit of irregular powder produced, which is very typical for for gas atomized powders. But we're encouraged by the flowability that we observed on these powders. And then in terms of the voids that are present in these powders, we see minimal amount of voids, but it's we do see some amount of inclusions, which we expect to optimize as we optimize the process parameters. And so generally, if we compare the plasma gas atomizer developed at RETEC with some of the other state-of-the-art reactive metals, the three key advantages that we see with this technology is that we can use a variety of different feed without having to produce a wire or a bar stock that allows us to then overall decrease the cost of the feed stock. Atomization rates can be high because we start with a molten pool that can be introduced into the atomization die, similar to non-reactive processes for nickel and copper. And overall, the cost per kilogram of plasma gas atomization technologies at scale is an interesting value proposition for this technology. So in general, at RETEC, we focus on supporting the industry not just today, but as we anticipate the industry growing over the next 3 to 5 years. And we've identified need for reactive metals, which we think we can address with the plasma gas atomizer. We continue to support the industry with large production scale atomizers for nickel and steel, as well as titanium. And then we see that there's a need for new entrants in the powder market, as various different printing technologies require some process development and maybe tuning of different powder classes. A small scale atomizer would be ideal for small process development efforts, and we supply that as well to the industry. This is some images for what a typical atomization system would look like. On the left, you can see that is a melt chamber, and the scale can be relatively large. You can see some folks standing next to the melt chamber at the bottom left. The center image is a copper cold wall melting for titanium. And then on the right, we have a electrode melting system. So to give you a sense of what typical atomization systems look like. And then finally, the industry is moving towards efficiency, lower cost, as well as high performance powders. And the way we achieve that is with a circular economy, a circular process. Normally powder production would require us to recycle the feedstock and be able to reuse that out of spec or oversized powders that are produced typically in an atomization process. And so it's important for us to consolidate that powder and then bring it right back into the feedstock. And then RETEC, as well as other folks in the industry, are focused on being able to reuse and recycle this material back into the atomization process. So with that, I'll summarize that there are strong drivers for AM-specific powders. We've done quite a bit of work over the last 150 years developing powders for press and sinter, but there's more work needed to be able to tune powders for specific for additive. The powder production process is selected based on the powder specification. So not all processes are equal. It's depending on the end powder requirements. Different processes are suitable. And then there are many mature atomization techniques available, but there's continuous work in making improvements to fine powder production or producing reactive and refractory metal powders. And RETEC is actively developing new techniques and technologies to meet future market demand. So with that, I'll end my presentation and send it back to you, Marcin.
Thank you very much, Amir, for a very interesting presentation. Now, when we have a better understanding about this manufacturing process, we can see how many factors play an important role in this process and how important it is to have also a good quality equipment and specialized support during startup and implementation into the production phase to be able finally to produce a good quality fine powder. I have a question for you, gentlemen. I would like to know your opinion. Can the powder road of manufacturing of the parts replace more traditional fabrication methods like forgings, castings, and so on? And what is limiting us in adoption of a large scale of using additive manufacturing?
I can try to answer that.
Okay.
And then Todd, of course, please give us your thoughts as well. Essentially, in one word, it's cost. So the cost of the additive manufacturing process, the cost of feedstock, and the cost of post-processes all have to be considered when we are trying to evaluate whether additive is a suitable process for a certain application. I also would remind the audience that additive is a tool in our toolbox. It is not, in my opinion, my humble opinion, a process that will replace traditional manufacturing such as forging and casting. But I think it's an excellent tool for certain applications where we need to consolidate multiple assemblies into a single assembly, need some certain physical characteristics, whether it's heat transfer or cooling requirements. So there are some niche areas where additive is not replaceable by traditional methods, but it is not a solution for all technologies or all manufacturing processes.
Yeah, Amir hit on my major concern with a lot of the hype that's out there on additive being able to replace a lot of these techniques. It is a tool in the toolbox. But adding to Amir's comments on cost, I'd also bring about the scale of the processes. If we look at the amount of material produced by or used in additive manufacturing, and I can only go back to about 2018, 2019 pre-pandemic levels, where you were seeing about maybe 2,000 metric tons of metal powder being produced for additive processes. At that same time, there were 93 million tons of steel, structural steel produced, whether it was for automotives or structural applications. So the scale of industry and this concept that additive would be there to replace all of these traditional processing routes is rather, I'll be blunt about it, rather foolish that's out there, and really not understanding the scale of what manufacturing is. And I think that's something we need to take into account. The other one is really goes back to a lot of my points, is that the properties of the additive materials have far too great a levels of uncertainty, and the uncertainty quantification hasn't been performed that they can be inputted into critical applications right away. I think that's something that we really need to sort of keep in mind, is that the casting and forging industries have about a 75 to 100 year head start on producing consistent properties. And additive has probably, since the latest version of it, about 7 years. So they still have a pretty long way to go to develop the databases.
Okay, thank you. You mentioned cost is one of the items that is driving our selection of the manufacturing method. What inputs determine the cost of additive manufacturing powder?
So feedstock is very important. So the type of feed that goes into melting before atomization is critical, as well as the ability to be able to recycle oversized powder. As I mentioned earlier, for additive manufacturing, the powders produced are broad distribution, and to be able to apply all of the powder to processes is usually not how the industry operates. So we have to be able to recycle and also have a low-cost feedstock and a variable type of feedstock, whether it's scrap, ingot. The ability to be able to use a variety of different feedstocks is going to be important.
Okay, thank you. Todd, if you can summarize for us, what are the most important characteristics, parameters of the powder for various additive manufacturing methods?
I usually start most everything by talking about composition ranges. And really that is sort of the starting point. A lot of my research and a lot of what my students are looking at really involves how small changes in composition. Now, what we're typically doing in the additive field when we're specifying materials is we're simply taking wrought and cast alloy composition specifications and using them. And I think as we develop a greater technical database, we can start looking at refining those for additive. Now, most companies are already doing that. And I think Amir can address this, is that each customer comes with the very specific needs that they want. And they're asking Amir to tailor his heats to what they're looking for. And he's probably getting 10 different customers coming to him, demanding different ranges of alloys in really the same grades. That is one. I think my concern is that I don't have a real good answer for you as far as the powder properties for specific powder-based additive manufacturing processes. I can't say whether Hall flow rate or apparent density or tap density or angle repose or which rheology tool is the best on what the properties are. And I think that's really a knowledge gap that's hindering the development of the standards and specifications that are necessary to further the industry. The industry is going to have a real hard time moving forward unless they really develop the strong standards and have the technical underpinning to those standards that you see in sort of the cast and the wrought and the traditional industries. We tend to think of these traditional metals industries as being old, but there is a wealth of fundamental knowledge that is unfortunately being lost at the universities, that we're not teaching these things anymore. And a lot of it is applicable to understanding additive as well.
Yeah, I would second that. We are definitely at a crossroads where we're trying to understand the specifications that are required, and then on the other side is the speed to market. And we're trying to balance that right now as an industry. We have, of course, certain alloys that we use as workhorse additive alloys, whether it's Ti-64 or 316 stainless, etc. But I think there is a balance between having appropriate alloys for additive and then speed to market. And that's kind of where we are.
Yeah, and I'll piggyback on the speed to market issue, and a concern that I have is that the nature of the components being made for additive processes, really, especially when we look at topological optimization, we look at some of the design features that are integrated into them, they're being inputted into critical applications. And these are ones where you're talking about need for, Class A, Class B type aerospace applications. And they are very susceptible, with the levels of uncertainty that we have, they're very susceptible to catastrophic failures. And additively manufactured parts, especially in the initial testing, do not have a real great track record in things like fatigue. And so if we rush to market with additive processes, there's certain risk levels that I'm not sure are well developed across the markets and by the designers.
Okay, just a last question because we are running over time already. So you showed us, Amir, some of the pictures of the equipment at the end of your presentation. If you can briefly summarize what are some of the new equipment that RITEC is working on to address the current and anticipated powder demand for additive manufacturing?
Right. So the area that RITEC is focusing on is listening to the voice of the customer. Our customers come to us and tell us they need flexibility in the feedstock, so we design systems around that. We're also developing atomizers for reactive and refractory metals because there's a lot more demand for harsh environment applications. And so we're focusing on that, as well as we're supporting our customers that are new entrants into the marketplace with a small scale atomizer. So hopefully that kind of gives you an overview of the various different areas in which RITEC is trying to innovate and support our new customers as well as existing customers.
Okay. Thank you very much. Thank you very much, gentlemen, for your presentations. Thank you very much for the discussion. I hope our audience enjoyed. We all learned a lot from this panel session today. I invite you for the next year e-seminar, all the audience. Thank you, and see you next year.
Well, hello and welcome from my side at the SECO Warwick eSeminar 4.2 Heat Treatment and Metallurgy. My name is Christoph Bolgen and I'm glad that I'm able to speak to you today. I work at JUMO Fulda as a market segment manager for industrial furnaces. Here my small agenda for today. First off, I like to introduce myself a little bit. Then we jump right into an example of a discontinuous furnace, a chamber furnace. Then a small example for a continuous furnace, a belt furnace. After this, I would like to show you the whole JUMO product portfolio, which we can use for the whole system solution. And after this, at the end, I would like to tell you a little bit about our calibration service. Here, as you can see, this is me, Christoph Bolgen. I started off as an apprentice, as an industrial clerk. After this, I started my bachelor degree in industrial engineering, specializing in automation and robotics. After I finished this, I went into the USA and did my master's degree in industrial engineering as process optimization. During that time, I worked as a service technician for burner systems. After I finished my master's degree, I started at the subsidiary at JUMO in the US as an application engineer. Since 2017, I work at JUMO Fulda as a market segment manager for industrial furnaces. Now enough of me. Now I would like to jump right into the example of a discontinuous furnace. Here you can see a chamber furnace, which is electrically heated furnace for processes in tool making and hardening, such as annealing, hardening or forging. It is a one-zone chamber furnace with a temperature time profile can be run through it. Here we use a temperature below 450 degrees Celsius. As you can see, we have here a separate controller, our Diratron single loop controller, and a separate recorder, our LogoScreen 600. We use, since it's such a low temperature, below 450 degrees Celsius, a single or double resistance thermometers with a SAT test hole. Then we use a TYA power controller to reach the accurate temperature. To monitor the over temperature, we use our certified safety temperature limiter with certified resistance thermometers. If we use a single PT100 or PT1000, then it's CL2, and if we use a double PT100 or PT1000, we get CL3. What are important tasks for a single loop controller like the Diratron in this example? First off, it needs to be precise in control of the temperature and time-dependent processes. It needs to be easy to operate and an easy input of program steps and accurate sequencing of programs. It should have a high flexibility and integration, taking into account building and process specifications. If you want to use a single loop controller like the Diratron, according to those guidelines AMS 2750 and CQI, then we need to make sure that the inputs are as accurate as it needs to be, and we need to calibrate it upfront. Here you can see the compact system for temperatures for our over temperature monitoring. Our certified safety limiters, our certified resistance thermometers, and the whole documentation. Here you can see the TÜV Nord certificate is an independent body for the individual compact system. The manufacturer's declaration, in which the complete safety chain was evaluated, is also in the complete documentation. The whole chain is certified as CL2 or CL3, as I mentioned earlier. Now I would like to jump into the next example, the continuous furnace, the belt furnace. Here we have the belt furnace, which is continuously running processes with fixed cycle times, such as drying, preheating, curing, aging, thermofixing, vulcanizing, or degassing. If you have to use one of those processes, then the continuous oven are the right choice for you. Here you can see we have 5 zones, and each zone has its fixed temperature during the run when the product goes through it. During the time which the product goes through, it reaches the right temperature time profile. For this example, we use a temperature above 450 degrees Celsius. For this example, I would like to use our new automation system, the PLC, the Diratron 500. It is an all-in-one PLC which can be used for controlling and recording. Also, a solution can be the Yumo SCADA or the Yumo Cloud solution. In all those 5 zones, we use a single or double thermocouple with a SAT test hole, since the temperature is above 450 degrees Celsius. To reach the right and accurate temperature, we use in each zone a TYA power controller. And to monitor the over temperature again, we use our certified safety temperature limiters with certified thermocouples again. The whole entire measuring chain, from the sensor to the logic, safety temperature limiter, and internal relay 3 amperes are CL3 certified according to EN 61508 seal standard and the EN 13849 performance standard. Here we can reach the highest performance level E. The shutdown and signaling are done via safety related output. Use a SAT 2750 and CQI guidelines. can help you with the process engineering. Or the pistons. It's funny, but let's designer designs. Then the plant operator creates the programs with the program editor and the evaluation software and the SCADA system. And the operator of the systems makes the final products with the right values and the right screens of the Viatron system. Here you can see that we continuously work on the smartware programs to make the PLC even more customer friendly, where we have quite some nice solutions already for the industrial furnace market. And of course, all our sensors can be connected to our PLC system. Now I would like to show you what Jumo has to offer in the whole product portfolio range. First of all, you can see we have controllers, the Diratron, the Dicon Touch, the power controllers, and so on. Then we also have recorders, the LS Logo Screen 600 and 700. If you want to use one system and not separate devices, then we can use the Viatron system, the Viatron 500 or 300 system. There you can have the control and recording function in one device. Measurement parameters are, for example, temperature, flow rate, pressure, and so on. But also we have analytical sensors, connectivity, pH, and so on, as well as thermostats. For temperature, normally we use thermocouples or RTDs. For the flow rate, we use our new Flowtrans US or the Pinus. For the pressure, we use the Ceras P21 differential pressure or the D-Trans P20 or the D-Trans P30. For the safety devices, as mentioned earlier, we use our certified safety temperature limiters and other safety devices in our house. For the calibration, we in our house we use the thermocore for the TUS test and the BMX for the SAT and instrumentation test. As you can see now, we can give you the whole system solution. It can start with our products like temperature, liquid analysis, pressure, level, flow, humidity, controllers, recorders, automation, and monitoring. We can also help consulting of the CQI 9, 11, 12, 29 and AMS 2750 guidelines. We also have the service calibration service where we can help our customers out. And our engineering department can help with the whole system solution. There's one part we didn't talk about yet, and this is the service calibration, which I would like to come to now. Our calibration service, as you can see, we have the accreditation according to the DIN EN ISO IEC 17025, which is the German national standard. Here you can see also our laboratory identification number. We have a calibration range from -80 to 1100 degrees Celsius, and we can do on-site calibrations. Calibrations can consist of RTDs, thermocouples, data logging, dry well calibrators, climatic chambers, temperature, display devices, simulators, analysis, pressure, humidity measuring technologies. We also do calibration as a service of third-party products. Cost-effective series calibration for platinum-resistant thermometers are also done in our house. And we also do the test equipment and calibration services. This is our calibration to our German national standards, which we are allowed to. For the industrial furnace market, there's another good important point, which are mentioned here. tests according to AMS 2750 and CQI 9, 11, 12, and 29. We also do the temperature uniformity survey, the TUS, and the system accuracy test, the SAT, with the JUMO thermocore test device, in order to achieve the required quality standards for the components to be manufactured in the series in a reproducible way. All those tests need to be repeated, as well as the control of the instrumentation, including the corresponding documentations, are required to pass an audit. That's where we can help as JUMO, as well as our colleagues at the subsidiary in JUMO Poland. We can do the temperature uniformity survey, we can do the instrumentation test, and we can do the calibration of measuring section from the controller via the measuring line to the thermocouples. We can do the SAT, the system accuracy test, and the monitoring test dates. That's where we can help out, because since the new guideline says external providers of calibration services must be certified to ISO IEC 17025 or another national standards. We are lucky enough that we have the national standard, the ISO IEC 17025 in Germany. So therefore we can do the external calibration at your house. Internal sources are allowed to do the calibration, this SAT and instrumentation calibration, but they need to work according to the ISO IEC 17025 or the national standard in your country. Well, thank you for listening. That's enough from my side. Here's my contact information, Christoph Bolgen, and my phone number, mobile phone number, and the email address. If you have any further questions, please feel free to contact me or my colleagues in JUMO Poland. Thanks again, and I wish you a good day, good start, and I hope you have a great further e-seminar at Secowork. Thanks again.